Hello, geology students. Um, Today I've been talking about quite a few topics. We started to talk about the Earth's interior. We got into a little bit about geophysics and looking how different P and S waves travel through the Earth's interior, and P waves. We found out that P waves can travel through both liquid and solids. We also found out that shear waves or secondary waves cannot travel through liquids. And basically, these waves have allowed us to interpret that the outer core is a liquid and that the inner core is a solid. So these waves have kind of revolutionized and have helped geophysics, figure out these problems of the Earth's different layers. So this is also an indirect method because we have to use part of the these waves, energy waves. So here, we also talked about the magnetic field, and this is where I kind of left off. We were talking about how rocks can record the magnetic field. So here's kind of a diagram showing that when a lava erupts on the surface, and basically all those iron or any magnetic minerals that are in that lava, what happens is they actually reorient themselves in the direction of the magnetic field. And this is what's showing here. These are probably magnetite minerals, and this line represents a vector which has direction and magnitude. So basically it says right here the magnetic alignment is preserved in magnetite, and it records the orientation of the Earth. So here's this larger yellow arrow represents the direction of the Earth's magnetic field. So it essentially parallels that, and that's really important because we can use this to determine if there was a magnetic reversal, and we can use this for other reasons as well. So here is an example of, I was just talking about magnetic reversals, and here's a perfect example of that showing. So here's the yellow arrow represents the present orientation of the Earth's magnetic field, and this is a lava flow 1, and then probably a lava flow 2, 3, 4, 5, and 6. So there's kind of a succession of lava flows, and in this first layer, it looks like that these minerals recorded basically an orientation parallel to the present orientation of the Earth's magnetic field. However, down in this little, in lava floors 4 and 5, it shows a reverse orientation. So these rocks here record a magnetic reversal or a change in the orientation of the magnetic field. And this is important because we want to essentially track this through time. So here's basically a magnetic strength map of Wisconsin. And this essentially, like a large magnetometer, was basically what they can do is they can do airborne magnetometer. What they'll do is they'll fly a plane that has either a device underneath the plane, and they can actually measure the magnetic field strength of the Earth. And here's where they did Wisconsin. And here are the magnetic field strength from all the way down to a negative 52 to a positive 1057, which is in these kind of these really, I guess, pinks, or I would say pink. And there's some important features on the Wisconsin map that to me right away shows a really important structure, which is this structure right up in here that is at the boundary between Wisconsin and Minnesota, and that is the Mid-Continental Rift. And that happened, I think 1,100 million years ago, when the continent basically rifted apart. And it never came to the stage where it formed an ocean basin, but it failed to that stage. But anyways, it's a huge magnetic anomaly here. All of these hot pinks are really high magnetic field strength. So here there is also some magnetic anomalies, and I believe these represent really high strength lava. These are lava flows, because we know that basalt carries a lot of iron content, and those are going to be the the strongest ones for magnetic field strength. But yeah, we have a lot of these little. This looks like a little crater type. A lot of little donut shaped things. I don't know for sure what these are, but you have, so you got to remember during the formation of Wisconsin, remember the Pinocchian orogeny. A long time ago here, we had these large mountain belt that ran through here. Also in Wisconsin, we had an ocean basin, so we had a lot of limestones and dolomites, and then we had this continental arc collision that formed the Pinocchian mountain belt, and so there's a lot of different I guess amalgamated terrains, you could say, different through time here. But this just shows the magnetic field strength. So here's kind of a sequence showing the magnetic polarity, and showing the Quaternary is the period that we're in, and it goes all the way back to the late Jurassic. And we can look at this is an age in millions of years. It goes all the way back to, what is it? Looks like 100 and this is let me see here. So this is age in millions of years ago here, and this represents the magnetic polarity. So we have, basically, this is just showing that we have changes in magnetic polarity through time. So this one would be, I think the black represents normal polarity, and the lighter color represents reverse polarity. So yes, so here's kind of also emphasizing how they call them magnetic stripes that form over time. So for instance, let me get this out of here. So here we have a mid-ocean ridge, and we have new lava that's basically forming. And at that time, what's going to happen is it's going to lock in. At that time, it's going to lock in the Earth's magnetic field. And here it's showing you through time that here's a positive magnetic anomaly, and then all of a sudden here we have a negative and positive, and we got negative. So we can essentially record. This is the magnetic profile is recorded by a magnetometer of the ocean floor, and here's basically at 0.5 of a million years ago, we have normal magnetism here, and then here we have a reverse at 1.5 million years ago, we have reverse polarity. So we basically it cycles through, normal, reverse through time. And these are all recorded in continental lava flows in the ocean basin along a mid-Atlantic ridge, or along a divergent boundary. So here's kind of showing you, so again, here your rocks are real young, and on the outer, as you go away from the ridge axis, the rocks are going to be getting older, and they're going to be recording different magnetic reversals through time. So that topic on magnetic paleomagnetism, we're done talking about that for now. And briefly, I think right when you guys started in lab, Jocelyn went over the term isostasy. What does it mean? Essentially, it's the equilibrium of adjacent blocks of brittle crust floating on the upper mantle. And we were talking about, this has to do with, something that has a lower density. Thicker blocks of lower density crust have deeper roots and float higher. And the example would be mountains. And then usually what happens is we need some things like to stay in equilibrium. And for instance, this is isostatic adjustment, is where basically it wants to rise or sink to achieve an equilibrium or balance. And this is kind of showing that over here, kind of here where you're getting more erosion because it wants to maintain a balance. And then we have also isostatic adjustment. During the last ice age, we had these really thick continental glaciers that covered the landscape. And what happened is, as the ice melted, what happens is the crust wants to rebound. And to this day, Canada and Europe are still rebounding from the last glaciation. And I think here it's kind of showing these red lines represent glacial rebound. And also, what I'll do is I'll stop here. I want to talk about gravity measurements and the importance of this. We'll get back to this shortly. So I'll talk to you soon. Bye.